Pause. Okay, a quick advertisement for next week's seminar. Glenn Wilson and Nigel Clegg on 3D real-time inversion of ultra-deep resistivity logging while drilling. And that's at 1400, so the same time a week from now. So today we have Kurt Strack, and as I said, it gives me great pleasure to have Kurt talk to us today on using high power control source EM during the energy transition. Kurt's got a long and distinguished career. He's president of KMS Technologies, does all sorts of integrated seismic EM, land, marine appraisal. And he's had a distinguished academic career in Europe, Asia, and USA. And you can see his CV on the registration. Over 200 publications, over 40 patents, member of many professional societies. SCG Reginald Fassbander Award for development through casing resistivity, a Russian Academy of Sciences, foreign member, and Kapitsa Gold Medal of Honor. Okay, I'm going to stop sharing there, Kurt, and invite you to come online and share your screen and give us your talk.
Okay, can everybody hear me?
Yep.
Good. So you saw the first slide. So let me just set the scene. And first I should say, I really appreciate the opportunity to talk to you. And I would, obviously I work for a company, so there's a lot of commercial intonation. I tried to play that down a little bit. And today I focused on high power CSEM land applications, in particular, since there is great opportunity during the energy transition. And we started building a land transmitter when we realized that not much had happened while we were doing something else. So the focus for the high power CSEMs is to reach a depth between 1,000 to 5,000 meters, which is the depth that is important for geothermal as well as hydrocarbon reservoirs. The other important part is, and Alan introduced the webinar for next week, which is about real-time application of electromagnetics. The important part is that the data that we acquire must be reconciled with something that the user trusts, and that is always the borehole log. At the same time, you need to get the results as close as possible to real time so that you can make operational decisions. That's where the value is of geophysics. If you produce the results 6 months later or a year later, then the value goes almost to zero, because nobody at that stage remembers what was done and may not be interested anymore. So the real value is to do things very quickly. Now we can do that today. It takes a lot of effort, a lot of money, and a lot of smart workflows to get that done, but it is in principle and has been possible for a very, very long time. Now I will talk about CSEM, and the reason why we talk about CSEM, because in CSEM you have the multi-components, and while magnetotellurics is biased towards conductors and horizontal induction current flow, in CSEM, the controlled source electromagnetics, for those new to these webinars, when you bring your own source, you also generate vertical current flow, and you can look at resistors, which is hydrocarbons, by using the electric field, and conductors by using the magnetic field. And in marine, mostly the electric fields are being used, the magnetic fields are also being used, but they're not as commonly used as the electric field, because the target for marine CSEM is in most cases hydrocarbon related, and hydrocarbons, oil and gas, are resistive. So that's just the introduction. And when you do measurements, you have 3D structures and you really don't know how your reservoir behaves in reality, even though you have an idea before you measure. So you really want it all. You can't really go back and redo the measurements. And then when you have only used one component, then you would have to do the other one. So I've seen some of my colleagues doing some reservoir monitoring baseline measurements in some big countries in Asia, and they only measured the magnetic field and the target was resistive. So you have no baseline. You cannot use CSEM with only magnetic fields to look for resistors. That just won't work. And vice versa. Now, when you go below 1 kilometer, you need a high power transmitter. So you need something above 100 kilowatts.
Kurt, you're not showing your PowerPoint. Do you mean to be showing it right now?
Yes. Why am I not showing my PowerPoint?
You have to share your screen again.
I have to find the Zoom window for that. I am on Zoom and somehow back to meeting, no, back to meeting. Here is the meeting, yes. And I am sharing the screen. You see it now, correct?
Yeah, not in presentation mode yet. Okay, now it's good.
So this is the slide that you didn't see. I just recap, we are focusing on reservoirs between 1 kilometer to 5 kilometers. To get there, you need high power above 100 kilowatt. We now are pushing 150 kilowatts. In reality, you probably need even higher power than that, and we can do that. My problem is always, since we are a company, to do that reliable, safe, so that there is no accident happening. And at this stage, we can only commercially risk 150 kilowatts. And I gave you before the introduction about MT versus CSEM. And so you really want to do all. And when we do CSEM, we always carry out MT right along with it. If not over during nighttime recording, then we do it separately before the survey. I strongly recommend to all of the CSEM users to use an MT system and just record the entire time. And when they turn off the source, they get MT data in the same acquisition system. And that works quite well. Now, how can electromagnetics support the energy transition? There are many applications, and Alan has been focusing on the mineral application. So I'm sure he has also looked at lithium mining, where EM is really essential. But I will look at something in between 1 to 5 kilometers. And I think the most important application is going to be carbon storage. And the reason why current storage is so important is because seismic is very, very limited in mapping the injected CO2. And in renewable energies is, of course, a geothermal exploration, we all know, and Steve Hallinan gave several examples, but monitoring geothermal can also contribute. The most geothermal production require induced seismicity monitoring. And in most cases, not much is being done with the data, but in reality, they should also monitor the electromagnetic response. In all cases, we see that seismic responses coincide, or actually the EM responses are a little bit before the seismic responses. And there is a petrophysical explanation to that. So we strongly encourage in geothermal for people to monitor the electromagnetic as well as the seismic response at the same time. And a lot more will be done in that area. A lot of the data just sits there, so eventually people will interpret it. Now, how do we go towards zero footprint in the oil industry? We will still be using oil for a long time to come. And the problem with oil reservoirs is that we don't take a lot of the oil out of the ground. So we are actually having a fairly high carbon footprint in producing the oil. And if we can increase the recovery factor by, let's say, 20 to 40%, which are huge numbers, then we are significantly lowering the carbon footprint. And we use the term EOR plus, and that's what I will be talking about here, which is essentially using CO2 injection to drive the oil out of the ground. And so you can also get the carbon credits, and you can actually significantly reduce it. The customer we work with in North America is a lignite mine, and they desperately need the carbon credits and the injection in order to keep the mine open. Otherwise, they will have to shut down. So there is a lot of economic drivers behind it, and these economic drivers are essentially coming stronger daily. So in the carbon capture scenario, we are looking for reservoirs, and we are looking for reservoirs because we know that they have a seal, and the carbon that we capture in the ground doesn't automatically go up to the surface. And so these reservoirs are in most cases known reservoirs. We are trying to inject into the saline part of the reservoir, and all of the discussion I'm having here is actually focusing on injecting directly into the salt water, saline, the brine part of the reservoir. In the oil-bearing part, the petrophysics would be slightly different, and we would have to look at some more complicated model evaluation. Then I've talked before about the EOR part. Here's a cartoon on the top right, and I hope everybody can see this. You are injecting essentially through a borehole the CO2, and then you have a zone where the CO2 is mixed with the brine, and brine in the subsurface has always high salinity, which is also important, because then the mixture of water and CO2 becomes resistive. And then you are pushing essentially the oil, and you get additional recovery. The advantage for oil producers and the disadvantage for EM geophysicists is that you can push the oil with almost anything. Anything you do to increase the mobility of the oil will make it flow, and you will enhance the oil recovery. So steam, hot steam is very common, but it's expensive. You can also use production. There are places where heavy oil, they use essentially a coil, a solenoid, plugged into a 50 or 60 hertz outlet. It just has enough resistance that the wires don't burn through, and they heat up the casing, and the oil starts flowing. So there are many, many, many ways to do enhanced oil recovery. And in the geothermal case, on the left side, we have a typical geothermal exploration section. And the academics use a different color scale. In the industry. What happened? In the industry, blue is like water, conductive, not because of some fancy definition, simply because of the dominance of Schlumberger in the logging industry. And nobody can imagine that water or blue is resistive. So that's why when you see commercial applications, we always have to make blue the conductive part and red the resistive part. So this is unfortunately, that will never change. So you will see in all presentations different versions at different places for the younger ones. Now, what I said before is the monitoring of induced seismicity. As geothermal becomes more common and gets closer to cities, and in Europe, in particular in continental Europe, every reasonable sized city with a reasonable city budget is trying to have their own geothermal power plant. And so they are producing hot water, and they're re-injecting the water. and they're not always closed circuits. And so in this case, the rock acts as buffer, and it then can cause a lot of induced seismicity. When the rock cracks, you have sinkholes, or you just have houses disappearing. And some of you may be aware of cases where this happened. Again, for carbon storage is the monitoring of the carbon dioxide injection and how it develops. We do not want that plume to disappear. Let me also emphasize that it's extremely important to monitor the seal integrity at the same time, so that the seal does not break. So when you monitor CO2, you should always put up a microseismic monitoring network, and our system can record microseismic and electromagnetic data for that reason at the same time, so that if that's what you wanted to do, you could do that. And again, I've talked about these two, so I just go on to the next slide. The basic building blocks of the system, which you lay out in many cases as an array, are receiver box with some sensors on the side, and here are some pictures of the electrodes, the magnetic field sensors, and we also have some small flux gate sensors. So these are the higher frequency ones, the lower frequency ones. We also have a broadband one. This way you can cover a frequency range. I'm sorry about these slides. It happens when you have all of these different devices. And the advantage is that you can go to very, very low frequencies with a flux gate sensor, and to very high frequencies up to the 118 goes up to 70 kilohertz. With the high frequency sensor. And so they can do all of this in one layout. And this is a geothermal picture where you have essentially the heat going into some, in a hydrothermal case, into a sealed reservoir, which is water filled. I took away the example for the hydrothermal application and put the monitoring one in, since I'm talking about monitoring. Then we are talking about more hydrocarbon applications for monitoring in this case. And we always use a cross dipole, and we operate both dipoles sequentially, and the data from the transmitter goes into the cloud so that we can look at it. And during COVID, it was quite good to have that, because the team looking at the data was located in Sweden, in Germany, in Houston, and at -20 degrees in North Dakota. And nobody could really go to North Dakota without 3 days of safety training. And nobody wanted to go through that safety training. And of course, and then the receivers, the data also goes to the cloud. For hydrocarbon application, we'd like to add shallow borehole tools. The advantages with shallow borehole tools, they can map anomalies with 10 times stronger signal to noise ratio, and they can focus the received signal directly below the receiver. We haven't done enough case histories to publish more about it than just 3D modeling. And here are then examples and pictures from the different receivers. Now we inject the square wave current, and with increasing time after switching, the current flows from one end to the other end. And for this dipole, then it goes downwards and outwards with increasing time. And this happens to be in the time domain, but you can also run the system in the frequency domain without changing any setups except the transmitter sequence. Now, the only time you will see me to say something between MT and CSEM, this is a general example. If on the left side you have a target and you have a depleted reservoir, this is what you would get with MT, and this is what you would get with CSEM, if everything works correctly. The proof is always in the pudding, and the operational efficiency and the reliable of the results is a different story, and that varies from survey to survey. There's a lot of people interaction there. Now, I have been messing around with high power transmitter ever since graduate school. I played with a 60 kilowatt transmitter. And right after graduate school, even before graduation, I ended up with a 0.5 megawatt transmitter in 1981. And then I've used different sizes. And we tried to reduce the transmitter size for safety reasons and ease of operation. And we came finally to the conclusion that we needed to go back to higher power after we had pretty much built acquisition systems that could measure anything we wanted. And we reached the limit of what you can do with the acquisition system. Now for monitoring, and I will get to it why, just a quick one, you need to get rid of as much processing and interpretation as you can. So you need to get the best signal to noise ratio and leave up the error to the statistics, which means signal averaging. And you need to repeat the measurement, and you're looking for very small anomalies. So you need to get extremely reliable data with the smallest possible error bar. And unfortunately, geophysicists are modelers, and we always build models, whether it's for processing or for inversion. And by the time we've built a model, we've smoothed the data, and we barely ever get under a 3% error from our model itself. I'm not talking about the data error. The data error can be high or low. We all know that. There are a lot of things you can do. So this is the first. We should complain with Apple with these jumps in the mouse. This is the first 150 kilowatt transmitter in 2016. And then this was the one we installed in Saudi Arabia just last month. Here are some pictures. Again, transmitter receiver. This is the generator, which is in most cases a rental generator. This is the recording cabin, which has the switch box in it, which is the heart of it. In this case, it was minus 20 degrees C, so it was very important to have that. And then the receiver side is at the bottom. And one of my colleagues added these nice details to it so that you can actually see what's happening in that trailer. And let me see, mouse, screen, pointer options, laser pointer. There you go. And here you have essentially the same acquisition receiver can also be run in a transmitter mode and control the transmitter, where it not only generates the waveform and synchronization, but it also can, in addition to that, record whatever you want at the transmitter side. The data is streamed via this web access box to the cloud, and we keep this web access box away from the analog parts. As you all know, when you use a cell phone, boop, 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 you do not want to have that in the magnetometers. It gives you noise you don't want. This is the system just before it was shipped. It has 5 MT sites, and then the rest of it is all CSEM. Of course, the receivers can be used for both. This is the system in Saudi Arabia. This is a 180 kilowatt generator. The second box is a fuel tank for the generator. And these are the generator watchers. They couldn't avoid some cable, heavy duty cable getting lags. This is the transmitter waveform you can select, and you can shape the transmitter waveform whichever way you want. This happens to be the time domain waveform, but this can also do time, frequency domain sequencing, IP and frequency domain, whatever. And here you see the back of the front is of course hidden by the dust because you are protecting the transmitter fan from sucking in the sand. And here is the back. You can see these are the 3-phase cables from the generator, and these are the electrode cables. Now in Saudi Arabia, we could easily get 300 amps in the ground. We ran the transmitter at 250. But at 300 amps, the fuse trips. We've set it up that the fuse trips and everything should be safe, that nothing breaks. There are many, many, many ways to do this. So in the carbon capture, what you want to do is you want to have a baseline measurement, and that's a measurement when no carbon dioxide has been injected. And this baseline measurement essentially measures the condition of the reservoir. In our case, you would get a CSEM induced voltage, and this looks to me like being a magnetic field. And then, let's say 2 years later, you have injected CO2 and it has migrated out. According to our client in North Dakota, they say 200 meters per year. From my experience of looking at monitoring situations, the average front movement is 100 meters per year. So between 100 to 200 meters per year. And then you would like to see an anomaly. And so you get a small anomaly here, and we simulated some of these results. And then 5 years later, you get a bigger anomaly. And you have to see these changes. And these changes are very, very small. So you have to find them. Now, the area where we were is the Williston Basin. And in the Williston Basin, you have many interesting things. Not only do you have a lot of old hydrocarbon plays, but you also have a lot of oil shale, and we'll get to that in the next one. So what's happening in CO2? And there's a beautiful publication on this, is that the carbon dioxide is combining with the water and builds larger molecules or clusters, as my German-speaking American petrophysicist corrected me 3 days ago. Germans would use the word molecules. I guess in English, in America, they use clusters. And these larger molecules are neutral. They're not like water, positive or negative. And positive or negative means that you have electrons that can jump from one to the other. And this is why in reservoir monitoring, every time you are generating mobility of the fluids, you get a dramatic reduction in resistivity, because you are essentially making the water molecules touch each other and the electrons just jump. Then you are injecting CO2 and you're putting these big blockers in there. Just like in the picture before, you saw these camels blocking the view of the generator. So you now are obstructing the electron flow. Less electrons flowing means higher resistivity. So once you have a certain salinity, which in reservoir fluids you always have, let's say 20,000 parts per million and above, then when you inject CO2, the resistivity goes up by a factor of 6 to 50 times. You have to verify that with the logs. And unfortunately, you will have to verify that with the logs in every reservoir you are working on. So it's not like you've done it and now you know what to do everywhere. No. Petrophysics doesn't work that way. So, so this is number one. CO2 increases resistivity. A few years back, let's say 10 years back, we looked at some logs from the Bakken, which is also in that same area in North Dakota. And we looked at some CSEM 3D modeling at a reservoir. This is the reservoir itself. There is a current being injected at the surface here. And we looked essentially at a dipole be injecting current and receiver downhole. And you can see the fields being built up. Now, if you multiply these values that were calculated, this was with COMSOL, then you multiply them with the transmit and receiver moment, you will see that you are looking at values in the order of millivolts. So you are getting very, very large signals in the reservoir. And here the current is actually being channeled into a resistor, which totally surprised me. I did not anticipate that a reservoir this deep and this small would give us anything. Again, a picture of what's happening. You're injecting in this, you're developing this plume. When you are looking at the high-level basin, then you're looking at multiple storage opportunities, multiple reservoirs. And there is nothing more difficult for electrical geophysics than to map resistors under resistors. And you will end up very quickly using second derivatives in order to see anything below. So how do you do this? The first thing we do is we get the well logs and anything we can put our hands on, of course, the geology and seismic horizons, and we derive an anisotropic model. And here is the log and the anisotropic model. The blue one is the horizontal resistivity, and the purple one, or pink, is the vertical resistivity derived from this log. And there are ways to do this. They're not subject in this presentation. It's written that up many places. And then we determine what variations we get, and we do a fluid substitution and evaluate. But in addition to that, we go to the field and measure the noise with the sensors we have available. And we take as many sensors as we can in order to find out which sensor is best. And here, this was done, and you have essentially the variations for different offsets from the transmitter. The transmitter is here, and the receiver lines are these red lines. This is the proposed injection side, and there is a second transmitter here. And so you vary this, and then you compare, in this case, the power spectrum is different filtering directly with your modeling results, and you are always trying to be above this. And we had the choice here. Do we use coils, vertical coils, or do we use air loops? And from normal considerations, our vertical coils are more sensitive. But from this process, our air loops came out to be more sensitive. And in most cases, they came out to be more sensitive. Advantage is also they're cheaper, but that wasn't the reason. So then the next question is, I go back, what is the spacing here? Now that's important because you have to mobilize, in this case, a seismic crew, do all of the HSE permitting to work in the field, and the HSE and the permitting. And all of that costs money and time. So you need to know exactly how you acquire it. And this is the baseline survey. You want to make sure you have sampled the reservoir sufficiently accurate that when you do inject, you can go back and build a reference to it. So getting reliable baseline data is of utmost importance. So we carry out usually a 3D feasibility. And I always like to decouple it from the survey itself because I want to be able to say no. And in many reservoirs, in fact, in more than 60% of the times, I've said no. I said, you should not do a survey. You only have a 5% anomaly. That's kind of low for using electromagnetics for the first time. And but here it was clear because of the results from the Bakken and North Dakota, the resistivities are very favorable for electromagnetics. So what we did is we took the 3D anisotropic model that we built from the logs, and we modeled different scenarios, different offsets here. And in this case, we looked at the reservoir at about 1.6 kilometer depths. It varies over the area between 1.6 to 2 kilometers. And you can see that in the data, but we assume it's at 1.6. And then we essentially modeled an injection radius of 150 meters and placed the receivers 100 meters apart on the left, 200 meters apart in the middle, and 300 meters apart on the right. We also did 400 meters, and 400 meters looked significantly different. The point I'm trying to make is that in all three cases, if you have sufficient number of offsets, you will be able to reconstruct these variations and the anomaly from each of the curves. And the changes from very dense to 300 meters are smooth. So these are all the same, and you could pretty much interpolate them. So if you look at this academically, you would say, well, 300 meters is enough. When you look at this commercially, you say, well, 300 meter may be enough, but we are doing 200 meters because we also are dealing with bad data. We want data redundancy. And so we picked the spacing of 200 meters. And this is for the Y electric field. And we did the same for the derivative of the vertical magnetic field. And it's the same results. You see an anomaly, and you can see the anomalies are small, 1.5%. And the anomalies get even smaller for the deeper reservoir, which is at 3 kilometers. And for that, you would have to pull some more tricks in order to get a better signal to noise ratio. The acquisition that was carried out afterwards was, we did MT, 42 sites, 600 meter spacing. So the green are the MT sites, a remote reference, 2 remote reference, one in Texas and one a few hundred kilometers to the north. Then the CSEM are in between, and where the MT is. There is some gaps here which you don't see where the point is directly on a parking lot, and there we didn't really get any good data. This is a power plant, so we had to run a line straight through the power plant. And this area is a nightmare because that's where the power grid comes into the power plant. The operation was 24 hours operation, 6 weeks continuously. I was quite pleased that we had no equipment breakdowns, operational equipment, you know, like the generator runs out of gas, out of diesel and stuff like that, or we swapped the generator with a spare one, things like this. But essentially our equipment didn't break down. We got the data in real time through the cloud, which I strongly recommend you try to do data telemetry to the cloud anywhere else but the United States, and probably also not in Germany, because the cell phone networks are terrible. Anywhere else it's easy. The production was, you could pick up 24 sites in one day and deploy 16, and you could fully record 17. And this of course varies because we had to give a green light from the quality assurance before they could pick up the receiver sites. This is a noise test. Notice that the web access box is right on top of the acquisition system. That's not always the case because it can generate noise. And this is night operation. So we swapped the crew at night and in the morning, and we kept the night crew stayed the night crew, and the day crew stayed the day crew, and it's the only way it works. So, and then this is the transmitter side. The transmitter sites were dug in the ground. I think they used 4 or 6 pits. The important part is that your transmitter electrodes are stable, that you don't develop any chemical plants, chemical reactions. And we actually, because of the environmental restrictions, and a lot of this is reclaimed mining land, we had to pull out the electrode sheets, and I had them take some pictures of them, and they were perfect. They were just like brand new after 6 weeks of operation. So it's always good to have more electrodes in order to make the plants more stable. In Asia, we could actually see on the transmitter, and they were trying to do the electrodes on the cheap side. And we could actually see when one of the electrode plates burned out and the current dropped with so quickly that the current stabilization, the transmitter is current controlled, couldn't catch up. So boom, all of a sudden you had some 10 amp drop or something. And this is the workflow. You set up the transmitter, you verify the transmitter. This is important when you use a seismic crew. They never give you time to verify the transmitter. Once the transmitter is working, they say, oh, let's start acquisition. You say, wait, I need at least 1 day to verify that everything is correct. We do have transmitter and receiver overprints, and things can go wrong. You can have problems with the transmitter, that the current from the transmitter gets channeled into something. You get some weird behavior. And if you don't have the time, you have to make funny decisions in order to keep the operation going. And then, of course, you lay out the receiver, you do the quality assurance before you pick it up, and then you move the receiver when you give them green light. And hopefully, we've tested the quality assurance to do that with machine learning and artificial intelligence. We have tested it and we think that it works. We haven't put that into production yet, that your cell phone would get a green picture and means pick up the receiver. We're still doing it with a person on the ground. Now, one of the problems is, how do you see all this data? We had a large data set, about 350 sites, transmitter receiver combinations, and each receiver has 5 components. The measurement error is less than 0.5%. And as I said before, the processing error and the inversion error or smoothing causes more problems. So you have to really make sure that your data is reasonable. And we spent about 4 or 5 months after we acquired the CSEM data to come back and essentially do no processing of the data except signal averaging. I wasn't touching anything. This is strictly my computer having its own life. So back to the slide. And so we avoid as much extra processing as possible, so that the only processing we really want to do to the data is the signal averaging, robust stacking, and as little filtering as possible. But getting there requires that you have to do a lot of different filtering to understand the data. And we're now matching the 3D models, and we are understanding what's good in the data, what's bad in the data. But if you have enough data, you can just move on. And you can use then the 3D model for making a calibration check on the data itself. And once you have all of this done, you obviously have to make the workflows procedurize, put it into some algorithm and do it in real time. So here's an example where we acquired a site, normal MT data, and we have a mismatch. The data is the dots, and there's a mismatch between the inversion response, 1D inversion, and the data itself. And when you apply the remote reference site, which there's nobody at the remote reference site for weeks, then this goes away. And the dashed line is the horizontal resistivity of the anisotropic upscaled log. And this is the inversion. And this is just the first pass of the inversion coming out within 24, 48 hours. And then this is the 3D inversion result that comes out later, which where you use less sites. And and you just try to understand, and then you can say, yeah, well, this is reasonable. Now, nobody is really trying to use the MT for the CO2 monitoring itself, but if I'm involved, we will always acquire the MT, because I don't think that that means that it should not be done. I think that people have just preconceived ideas, and I have been proven wrong several times in my life. And Brian Spies was the one who was most adamant about pointing out to me how many times I was wrong. So, and then of course the 2D model is also used for quality assurance. And this is the Williston Basin. The North Dakota area is around here, to give you an idea about the depth. Sorry about the scaling of these labels. That happens last minute when you do this. And you can see there is some structure, and we see some of the structure in it. For the CSEM quality assurance, we stack the data, and this is a typical magnetic field transients. For those of you that know it, it's a good looking one. And then this is inverted, and these are just fast inversions. They're not really tried to match perfectly. We have much better ones now, like 6 months later, we match this log much better, and we'll talk about that in a second. But it's not about matching the log, it's making sure that the data is okay and we can use that data as baseline. The interpretation will be done on the differences of the data sets, not on each of the data sets, because the differences will take out a lot of 3D effects and near surface effects, and you'll be able to focus more on the anomaly. So that's why we are not optimizing this. This is an electric field inversion, and you can see how the inversion model goes through the center of the data points. The error bars are high. These are the stacking errors. We're not happy with those error bars. They're too high to use them as weights in the inversion. And I can't remember what I did to get them better, because I had the same problem many years ago when I managed to use those weights to drive the inversion. But the 1D inversion is not really the solution here. And here again, we have the log in black, and this is a typical inversion. And when you see that you have between 1600 to 2 kilometers, the resistor, which is the reservoir that's target for the injection, and you have something below 1 kilometers. This is pretty much fixed, the depths to 1 kilometers. We don't see much above 1 kilometers, not because we don't have it in the data. We have no log information. And without log information, there's nothing we can calibrate. So we have to figure out how we can let the inversion play, but not overplay the near surface. So that's why we fix it. Now, when you have so much data, and we end up with about 3,500 inversions for this survey alone, independent, and then of course you can make joint inversions from this if you want to play the inversion game. How do you look at the sensitivity? So one way to do is you look at the eigenvectors for the inversion and the eigenvalues of each of the model parameters, which is resistivities and thicknesses. They're usually, I think it's hidden. There's usually up to here, you have the resistivities, R31. So the model has 31 layers, and these are the thicknesses, 32 layers, and these are the 31 thicknesses. And what if you don't do that, if you don't look at where it's biased, you want to have these like distributed like white noise. And that tells you that you have at the lower part of the section some sensitivity, and the upper part. What you really want to say is my data really seeing what's in the subsurface? And when it looks like this, it looks good. If it is bad, if some of the upper layers have higher eigenvalues, because then they're overemphasized and most likely end up in a local minimum. And we sometimes see that. So I see some of the eigenvalues or even some of the curves where I just say, this is bullshit. This is a local minimum. So you have to be able to see that, and you have to be able to see so many of them. And this seems to be one way to look at it. And then once we have perfected this, we would get characteristics out of this to automate it. Another way to QC the data is through 3D modeling. And this is the 3D anisotropic model that we derived during the feasibility. It's the same model. The model has never changed. And the response from the model at this site for the transmitter receiver parameters is in the dashed line. And the data is displayed here. These are different electric fields. And these are in different electric fields in Y direction, and these are in X direction. And the shaded area is the area below 80 milliseconds where we fix the model. And we really can't say much about the data because of system response and the way we set things up. And we don't need to. We know the reservoir response is between 1 second to 5 seconds. So we're really interested in this range mostly. And so that's what we are trying to play with, and need to verify that the data is reasonable. And we can then read from the 3D model the consistency and inconsistencies and see them in the workflow. And these zero crossings in the logarithmic domain are not always noise issues. Some of these can be signal issues as well. And we do see them in the 3D model response. I just didn't pick one of those as an example. I just picked one of the last ones. As a result of this, we keep reducing the processing, and we are automating the processing to get the data better and more suitable with the 3D model. I didn't show you the difference between 6 months of trying to do these matches, because you really have to be an expert to see this. So let's move on from CO2 to geothermal. And this is an example of a geothermal reservoir that's producing. It's one of the largest producing geothermal reservoirs in North America. I'm not sure to what degree I can show some of this, so that's why I'm a little bit suspected. It's a very low resistivity environment, and the worst part about it, it is an increasing resistivity scenario. So when you look at NDM, you say, shit, I'm not going to see anything there. Well, I only looked at this reservoir because some of those pictures you saw from 1981 transmitters were actually from there. We actually found that field then and drilled it. And then, of course, nobody knows that because the Department of Energy took that over and they lost all the records. And now the third owner afterwards is having a power plant there. And so this is very complicated to get an anisotropic model from, but you can. And then you look at the seismic horizon of the reservoir. You have a change in depths of this reservoir layer of 600 meters over 6 kilometers. So this is a significant change in the model. So you feed this into the model, fix the seismic horizon, and then take the resistivity and you change the temperature, and then you get some response. And it's the same workflow you saw before, except this is an older version of this. These are the receivers in the field, and some of those that have worked in North America, they will immediately recognize where this is. A beautiful place to stay over winter and Christmas because it's very nice and warm. And these are then the different sensors. And this is again the plot you saw before with the noise. And here's the plot from this one here, where we had different air loops and induction coils. And you essentially, this is the noise floor, and you're trying to get the one with the lowest noise so you get the maximum response. And one of these curves is warm, the other one is cold. And you want to get the maximum anomaly. And these are the different receiver points with the transmitter. And I didn't put the Google Earth picture on because I wasn't sure to what degree it could be known. This is now funny to have a layout right on top of a picture. So this is a transmitter site in Asia, the best transmitter site we ever had. And the foreign geophysicist had to give the safety students from the oil company a safety lecture. I wasn't prepared to it, but I guess they wanted to talk to a foreigner. And the most impressive part here is the generator, the auxiliary generator, recording cabinet, workshop, was the water closet that they had installed here. This is in the middle of an oil field. And everybody runs around with ox carts, and you are right there with a high-tech installation. This is the oil field at 2 kilometers depths. They are injecting into producing reservoir water, and they literally inject water, 8,000 liters per hour, I think. So quite a bit through horizontal wells that are far away from that transmitter side. The receiver side was about 2 kilometers away from the transmitter side. And this is a time variation in the signal, pre-injection and post-injection, right where we predicted the reservoir influence was. And this is the anomaly, 30%, right above the water injection. The system, this was only a 100 kilowatt system. No transmitter. Yeah, the transmitter's in the box here. So this is the transmitter box. Was too heavy to take out, I guess. Here's the transmitter. There used to be a picture right here of the transmitter, which I guess will come with animation or disappeared in preparing this lecture. There it is, the transmitter. So the transmitter is 100 pounds, and this is the faceplate. It's tall, but you can lift it up. You surely need 3 people to lift up the 150 kilowatt transmitter switch, the switch box. Best you use 4 people. This is the data we acquired: electric magnetic field and 3 component geophone data. And Andri processed the data as a student, and we did a lot of filtering and stacking and post-stack the standard way. And today we would do this all different. We would approach this project completely different. Then after 2 days of water injection, we saw an anomaly of 30%. 200 meters away, this anomaly is significantly smaller. And if you wouldn't know where the reservoir is, you would not see anything 400 meters away. So what that tells you is you really have a localized change of the resistivity, and you can't really go further than the 200 meters away. So we went and we tried to verify this with 3D modeling, and we calculated numerous lines. The lines are here in white so that you don't get distracted. It's only 2 kilometers to the transmitter. So distance between, offset between transmitter and receiver is approximately the depths of penetration. And that's where Brian Spies won when he told me you are full of it. The time a target shows up in time domain is always the same, irrespective of offset. So that means at any offset, you can measure everything if you have a good enough system, powerful enough transmitter, good enough receivers. And he's right. I mean, he's absolutely right. I confirm that every time. Hard to understand. So don't read that part in my book where it says that the offset is crucial in survey design. It's not. So then what we did is we modeled this, and we get for the magnetic field directly above, we get 2% anomaly from the 3D model. And far away, we get also still a 2%. And we ask ourselves, what's wrong with this? And we talked to some of our colleagues at Chevron, and they said, well, you know, we have the same problem. The anomaly that we measure is higher than the anomaly that we model. And that may be due to current channeling of the pipes. Well, there's hundreds of horizontal pipes, and in fact, the water was injected from 6 kilometers away horizontally at 2 kilometer depths. So we modeled the casing, and I came to the conclusion that the casing modeling we see in the literature is wrong, because we use realistic values that we got from the feasibility of through casing resistivity tools, and we could not verify the pipe influence in the data. We see pipe influence, but not in the same bandwidths. And so we scratched our head. Why is this anomaly higher? And the only explanation is that we have heavy current channeling from the transmitter straight into the water flood, and that the current is essentially being enhanced by the water flood. Now, we've done some model studies for shallow borehole tools and focused source EM for the same area, the same models. And we see a signal, an anomaly enhancement of a factor of 10 through focusing. And of course, current channeling is nothing else than focusing with either differential receivers or using a shallow borehole tool, vertical electric fields. So that could be an explanation. I'm not saying it is the explanation, but it's the only one that really holds. Now, what will the future look like? And EM has a clear contribution to make to the energy industry, in particular, since in a CO2 scenario, there's very little impedance contrast between CO2 saturated reservoir fluid and original reservoir fluid. So fluid imaging requires EM. And when I say EM, I always recommend to record seismic at the same time. And when I say CSEM, I will always recommend to not forget to also acquire MT data. You've got the system there, so why not do it? Be stupid. The only problem is we need to produce the results faster. And of course, once you have a project, even if it's an R&D project, the minute you go to the field, everybody is pushing to get out of the field, and you have to really focus on delivering fast. So quality assurance and calibrating the data back in almost real time is very important. Well, that's not so easy because 3D modeling, as everybody knows, takes time. You don't do 3D modeling in 1 to 2 hours. You may run some models, but then you have to plot the damn stuff, and the plotting takes longer than running the models. And so the modeling is in many cases the bottleneck. So we desperately have to replace the 3D modeling through some artificial intelligence algorithm. It can be done. We've done it before, so it's not like it's new. And the quality assurance, which is holding up the survey, needs to be faster than within 24 hours. We got the data in at night. 6 o'clock was shift change, and when the geophysicists that came into the hotel had all of the data and everything else, it was fine to give the feedback the next morning on what had happened, and they could move the receivers. But if the geophysicist was hungry and wanted to go to the free chicken wings at the motel party, and by the time he was going to bed, the quality assurance geophysicist was at Walmart buying his dinner, then you had a problem. So quality assurance in real time without people interaction is really important. And again, here's the 3D modeling. So the most critical path is to make all of this near real time. And I think we'll be struggling with it. We've been trying to work on this since the 1990s for logging. And you see next week, you have a real-time LWD presentation. This is something which was very common 20 years ago as well. But now people talk more about it. So it takes a long time for this to happen. So in the future, we will acquire denser data of both seismic and EM, and there will be a lot more being done, and the surface will be more integrated with the borehole. And also there is a strong integration of land and marine. And my colleague from Japan may be listening in. By chance, I read a paper from Japan where they're trying to go from land to offshore with CSEM and a transmitter onshore. And they were very strong about showing that CSEM is so much better than MT. I wouldn't be so strong. So this bullet point was put on there before I read that paper in geophysics. And with this, questions. Thank you for your attention.
Well, thanks very much, Kurt. Absolutely wonderful overview, particularly, you know, it's good to see, it's excellent to see how EM can be solving these real world problems that seismologists have been working on for years now, and we can make a contribution. Okay, I'd like to open it up for questions. Please put your questions in the Q&A and then I'll read them out. And while the questions come in, Kurt, maybe I'll ask a quick question if you don't mind, and that is the shape of your transmitter waveform. I know from having been at Toronto that Gordon West developed the triangular shaped waveform for his UTEM, because of course, if you put that in a loop, you're measuring the time derivative, right? So that gives you a square wave for the electric field. So, and he was telling me how difficult it is to design a square wave source, an accurate square wave source. It's just so much easier to design a, you know, in hardware, design a triangular source. Have you ever thought of using a triangular source?
I did when I played around with the triangular source when I was in Cologne, and we didn't finally do it. But look, the hardware design is not the issue. Today's switches switch instantaneous. We actually make the source slower in switching. The way we design it in architecture. Then the guy who builds the source is actually over 80 years old and has been building sources for us for 30, 40 years. So the source switches very fast. We slow it down because every time you switch fast, you get ringing. And there are things like overshoots or induction related ringing. We can use the source not only for a grounded dipole, but also for a loop source, because the way the sources are designed, they very easily handle it. That's not the issue, the fast switching. The issue with the source is the stability. You really want to make sure that your source is ultra stable. Variations in the source current, and when I see these CSEM, land CSEM source signatures shown by some of my industrial colleagues, I don't stand up and say your source is not working. But variations in the current is what you have to control in the data as well in the source itself. So we have a current control in it, which is quite tricky. And we slow down the switching for this range. So we switch within 2 to 3 milliseconds. We can make it much faster. And then it would be for shallower targets. So we can modify that. But we don't use 80 milliseconds of the front data, even though the source switches. And the source has been very, very, very stable. We've looked at the switching every time we monitor the switching for all the different sources. And all of the sources that we've built in many different places, whether that's in China or in Asia or the US and Colorado or Texas, high power, low power, bad generator, good generator, they all have very similar switching times because of the new architecture of high power switching. If you do it right, you can control it. And safety in the source and reliability is key. You do not want to have a question about your current stability from the source. So that's why you use also electrodes that are stable, that don't vary, that don't become galvanic cells and change the current. That's something that used to be common. So Aaron, a lot of things have changed since the 1980s. And the reason to use a triangular waveform is to have a smaller signal to noise ratio. And that may have been appropriate when you built your own equipment. When I was making the electronics, I don't think I know anything about electronics anymore. It's very scary when my electronics discussions contribute to a conversation with electrical engineers. I'm not an electrical engineer anymore. This was 40 years ago. So there are ways to fine tune the waveform. We can, with fine tuning of the waveform, get better signal to noise ratios out of it. We investigated those during our times in marine CSEM, and there are some EMGS publications they should have never made on waveform shaping to address that. So you can play with the waveform. We are not there to play with the waveform. We are more looking at operational concerns and delivering the data fast. At this stage, everything is fine. The key issue is the damn thing is safe and you don't get electrocuted when you touch something.
Yeah.
Which I think every electrical geophysicist knows how that feels.
Yeah, thanks for that. We have a question in from Ephemios Tataras, and I'll read that out so it gets in the recording. Hi, Kurt. Thank you for the great presentation. How do you see the use of CSEM in monitoring carbon sequestration, carbon storage after the initial injection is complete, i.e. not monitoring the injection, but the subsequent evolution? Is CSEM sensitive enough to detect changes, or will seismic be the tool of choice?
Well, Temis should know that because you worked with a large oilfield service company. So I got into this from the permanent monitoring side. The real future is to have permanently installed sensors in the subsurface. And unfortunately, the business model of the industry is not there to make money with it. This is why the monitoring industry has gone through 3 or 4 iterations in building up and shutting down in the last 20 years. So the value is in permanently installed sensors in the borehole. And of course, the value is to get near the reservoir with permanently installed sensors. The reason why I'm working with Lemma is because they're a sensor manufacturer and they can make many of these in many different sizes and we can put them in the borehole. So I see a real value in the permanent sensors more than doing it from the surface. I don't think you can do much from the surface alone. You need to go in the borehole. You need to get closer to the reservoir.
Yeah, I agree. SM Abode is asking, does CSEM get depths to 10 to 20 kilometers, as in the case of MT? What are the main differences between MT and CSEM? Is it only resolution?
Yeah, there are many differences. We had the 3D,
go for an hour on this.
we had the 3D model within a week after the survey was completed. We are still monkeying around with data quality with the CSEM a year later. No, less than a year, 9 months later. So there are many, many, many differences. It comes down to the practical ones and resolution, everything else. So Tillman, in his unfinished PhD, did a CSEM survey over the Kapwal Craton in South Africa. And I think Tian Leroux was also part of that crime. Both never really published it in detail. That went down to over 40 kilometers with CSEM and very, very small transmitter. So you can go deep if it's resistive. In a sedimentary basin where it's mostly conductive, and you are in Saudi Arabia, so you are dealing with resistivities around 3 to maybe 10 ohms. So 90% of your reservoir will be below 10 ohms, unless you go in the mountains. And there, CSEM would go up to 5 or 6 kilometers. I've used megawatt sources, but then you are using every day a tanker of diesel, and it becomes very expensive. And of course, that type of operation can get very quickly unsafe. Now, we've been good with field operations and we had strong HSE, but we do have accidents in the field. And luckily enough, these accidents are never related to the transmitter. They're always related to a car, a truck burning and disappearing, or some equipment all of a sudden gets stolen, or catches on fire, not related to the geophysics. So I cannot sell you a 1 megawatt transmitter and tell you it's safe and I will give you a warranty on it. You don't get warranty on a megawatt transmitter from me. I can build you one and you can have one, but you have to handle it yourself. I can do 200 kilowatt and sell it commercially. I'm now very comfortable with the safety concept. You can't get electrocuted. You can cut the wire. You can have children cut the wire with a knife during operation. Nothing will happen. We have safety things in place. The first time we built those safety things, the first thing happened in Bohai Sea in China. The whole transmitter caught on fire and all the safety devices were gone. So we operated 6 months without safety devices with spare parts. So those are the issues with CSEM. So you can go up to 4 or 5 kilometers with 200 kilowatt. I can make you a 500 kilowatt transmitter, but at more than 500 kilowatt, I think I will stop and say, not now. I have to make 3 or 4 before I can even dare to make something bigger. So that's where the problem is. And it, of course, they eat a lot of diesel. You don't want to pay $1,000 for diesel in Saudi Arabia every day.
Yeah, I think the other thing you could touch on, Kurt, is that CSEM is that is really the only technique to use in a culturally noisy and a very noisy environment. MT is useless in a lot of these brownfield areas, just too much contamination.
I should make you a sensor, Alan, that you can use anywhere.
But it's nothing to do with the sensor. It's all to do with the noise.
But there is a crossover. There's a crossover now. And also, the deeper you go, EM loses resolution. And whether you have CSEM or MT, when you are 5, 6, 7 kilometers deep down, what the hell is the difference at that depth? I mean, we had a farmer tell us in the German deep drilling project, and we were staking out every 20 meters a receiver point, or every 50 meters. And he looked and I said, are you nuts? 10-kilometer deep hole, 50 meters at the surface. You think your measurement 50 meters apart is different from 10 kilometers at the bottom?
Yeah, exactly.
So I think it's both have a place. And I like to tell people that I have been surprised by every joint inversion between MT and CSEM data. And there is philosophies behind it. And I've proven every one of the philosophies wrong by taking a different side where we had MT and CSEM data. The joint inversions are always fantastic. So you really want to look at everything. They're different. They're different methods to look at it. And you can also do some focus source EM imaging with the CSEM. You can do frequency and time domain. And, you know, the Chinese do TFEM, IP, time domain, and frequency domain. You can do it all. The important part is that you are finding the sweet spot with your measurement and your target. And you don't always know that beforehand. And that's why you are using the different techniques.
Yeah, exactly right. Glenn Chubak is asking, and hi, Glenn, good to see you here. What are the voltage limits of your source?
Our source is driven by the input voltage, again, for safety reasons. Any normal electrical conductor is limited to 1,000 volts. So I cannot sell anybody a 1,000-volt source and say it's safe, because you have to go to special connectors and it gets very quickly very expensive. A source like this is a few $100,000 already. So it gets very expensive if you want to go there. And then you end up hiring high power companies. And we have spent $5 million hiring high power companies in the US and in Europe. And they have all failed building a source like this. So it's not an easy undertaking. And my engineers tried this before and said, why don't you just hire one of these power companies? And they came back and they were 3 times as expensive and 5 times as big. We can, if you put a higher input voltage in, you can easily go up to 1,000 volts. And again, above there, you'd have to review everything, and you can, and it's mostly the connectors where you have to do it differently. I warn you at this power to not use transformers. You can use transformers. Every transformer I've used, and I've used in the 1980s transformers, and that's the first thing I threw away, because they're always caught on fire and you don't want to have to deal with the truck burning with a transformer on it. Transformers at this power rating at 40-degree ambient temperature will catch on fire quickly, very, very quickly. So you provide a higher voltage that doesn't go through a transformer, then you can make a source like this. The problem is the connector. But you can make screw connectors. You can take brass bolts and heavy wires and make sure that you have connectors that don't have those limitations. But again, doing this commercially, I had several incidents where the police shut us down and frogmen were in a lake looking to it for a 3-year-old child, and everybody claimed we electrocuted them. Your life goes by you, the 10 minutes when you go to the transmitter side, until later they find the child in another village. You don't want to have any accidents or anybody dying with the transmitter. So you have to provide this 100% safe. And I'm very proud that our source is 100% safe now.
Well, thanks very much, Kurt. It's we're an hour 20 in, and one final question from Jerry Roth. Hi, Jerry. Nice to see you here. Hi, Kurt. An enlightening talk as always. Any comments regarding the efforts to use cross-hole EM for better delineation of resistive targets?
Jerry, that's a non-commercial proposition. Why? You only have a small open hole reservoir zone in oil wells. Most oil wells are cased. So the only way you can use cross-hole EM through casing is with magnetic sources. You can use electric sources, but casing is 1 million times more conductive than the formation. So 1 million times more current goes back to the surface through the casing and nothing goes in the formation. So if you have an open hole, you can use cross-hole EM for this, but you really want to have also electric dipoles with it, or you use gradient magnetic fields to generate the same mode. You can do that. And we have used gradient magnetic fields as receivers to substitute the electric field. But to use it as a source, you really need the galvanic component. You need the DC component to get this mixed current flow. So delineating resistors with cross-hole EM is difficult because it's an inductive measurement and it's biased towards conductors. You can do it, because in 3D you can do anything and you get some sensitivity. But the better way to do it is surface to borehole. I hate to say it, but then you don't get the accuracy, or you do long spaced as they do in LWD. I mean, maybe Glenn will talk about the long spaced directional LWD tools. They are electrical tools, galvanic tools. So you can do it, but it's very academic, Jerry. It's not a commercial proposition because it's just too little open hole to run experiments. And there are no rat holes. Those that says you go below the reservoir zone and put your instruments in. Nobody drills below the reservoir. You have the higher risk to destroy the reservoir than putting an instrument in there. So once you have the reservoir, that's the part that stays open. Anyway, Jerry, you can email me if you need more discussion on that. Anybody can send me their questions if they want.
Well, thanks very much again, Kurt, from everybody listening and everybody who's going to be watching you in the future. As I said, I'll have this recording up on the YouTube channel and the EMinar page within a couple of hours, and then Kurt will send me the PDF. So thanks, everybody. Thanks, Kurt, and see you same time, same place next week. Bye now.
Okay, thank you.